What's up, everyone? Today we're going to do an interesting problem where we are going to implement a Java class that implements an autocomplete functionality. So what we're going to do is we are going to write a class called autocomplete, and this is going to have two things. It's going to have a constructor that's going to take in a dictionary, or like a list of strings, and then it's going to have a method called getStrings or getWords for prefix. And what that's going to do is it's going to take in some string prefix and it's going to return all of the words in the dictionary that start with that prefix. So fairly straightforward, and we can see in this example we have this dictionary here, and then if our prefix is A, then we return all the words that start with A. So we have ABC, ACD, A, and ABA, which is our output here. And then if we look at all the strings that start with B, we want to just return BCD because that's the only one in our dictionary that actually starts with B. So that's going to be that's our goal here. So let's go ahead and dig into what exactly is going to be involved in this problem. So first of all, we probably want to know what's going to be the format of our dictionary. Is it going to be like a file of words? Is it going to be just an array or list? Or how are we going to deal with this? And so in this case, I'm going to assume that we're just going to take in the dictionary as an array into our constructor. So we're not going to do anything fancy. I'm not really worried about file IO or anything like that. So we will just have that easily accessible to us. And then another question we might want to ask is, are we worried about capitalization, like uppercase versus lowercase? Or could we have strings or prefixes that have additional characters in them other than, alphanumeric characters or letters even? And so in this case, I'm going to assume that one, all of our characters are going to be lowercase, and two, all of our characters are going to be letters, and they're not going to be any numbers or dashes or anything like that. And the reason I'm doing that is just that it's going to simplify the code a little bit. You could certainly include those, or you could do various types of pruning or cleaning of the input so that wouldn't be a problem. For example, if the case doesn't matter, but we still have inputs that are both upper and lowercase, we could just lowercase everything across the board before we do any operations with it. So there are a lot of things we could do there, but I'm just not going to worry about it. And so let's go ahead now and talk about how we could actually solve this problem. And as always, the first thing that I would recommend is that we talk about a brute force solution, or think about, how could we get a solution to this problem even if it's not an ideal solution? And hopefully this is pretty clear here what the brute force solution would be. We can just take our prefix, so for example A, and we can go through each word and see if each word starts with that prefix. So we could do this a couple different ways. In Java we could say, just does the there's the Java contains method for a string, and you can see, does it contain each string contain the prefix, and is the start index of that place where it contains it at 0, right? You can see if it contains it at the beginning. You could also traverse both until you get to the end of the prefix and see if the letters all match. It would be fairly easy to do. Problem with that is that's not going to be super efficient, right? Because that's going to take proportional to the length of the prefix and the length of the dictionary, right? Because you have, let's say that the length of the dictionary is D. So the length of the dictionary is D, and the length of the prefix is going to be N, for example. That's going to give us big O of D times N, right? In terms of time complexity, because we're going to go through every word in the dictionary, and we're going to go through this is obviously making some small assumptions like that every word in the dictionary is longer than the prefix, but given that we can assume that as this is the worst case time complexity. So in this case, obviously, we go through every word in the dictionary, and then we go through every letter of the prefix to compare that to the word in the dictionary. And so that's really not going to be very time efficient. And we're going to have to do that every single time we want to find a prefix, or we want to find a set of words. So the real question is, can we do better than this? And of course the answer is yes, particularly because we can do some pre-processing here that will allow us to actually improve our lookup times dramatically. And so hopefully as soon as you hear prefixes, I hope that your mind immediately goes to using a trie or a prefix tree. And as hopefully you know, what that is basically a tree, and we are going to store the letters of the words in that tree. And so let's look at an example here. We're going to have some node at the top, which this is not actually, does not have a letter associated with it, but we're just going to have some root node. And then there are branches for each letter that we have. So in this case, the first branch is going to be for the letter A, and the second branch is going to be for the letter B. And so for every word that starts with the letter A, it's going to travel down this branch. And then we're going to have a node here. And then, of course, we're also going to have a node here. And so next up, we're going to go to the next letter. And so we have a word that starts with AB, and we have a word that starts with AC. And so we're going to add AB and AC here. So this is going to be C, and this is going to be B, and hopefully you can see what we're doing here. Basically, we're going to continue down. I'm not going to go through every one, but then we also have to mark each node as to whether or not it's the end of a word or not. So we're going to mark, for example, this node, we have our word that's just A, and we're going to mark this node as being, we can come up with some clever way to mark this. Let's just say that. So this node is now marked as being the end of a word. And so when we traverse from the top of our list down, we can see that, oh, well, here's a word. The first letter is A, and then we reach a node that marks the end of a word. So one of the words in our list is A. And then we would also continue down this way, and there would be another node here where there's no AB in our list, so that node is not going to be marked. But then there's an ABA and there's an ABC, right? So we're going to have ABA here and ABC there. So hopefully you can see what I'm getting at. And then these nodes are both going to be marked. And so by using a trie, we can easily look up whether the prefix is in the tree, and we can also store our words, our entire dictionary, much more efficiently. This is sort of a bonus points, is that you're basically compressing all the words. So worst case scenario, every word is completely distinct, or every word starts with a different letter, and so it doesn't save you anything. But in the average case, where you have a lot of words that start with A, now all the words that start with A, you only have to store that A once. And so by using this trie, we're going to make it a lot easier to look up the prefix. And so it's easy to find whether the prefix exists in one of these words. But then what we really want to do is find what the words are that start with that prefix, right? And so we have two options here. The first option that we have is at each of these nodes, we could store a list of every single word that starts with that prefix. So in this case, we would have a list here of, we would have a list of A, we would have a list of ABA, we would have a list of ABC, and we would have a list of ACD. So all we would have to do is traverse, if our prefix was A, we'd traverse to here. We'd see we'd traverse our full prefix down, and then we'd get that list, and we'd just return the whole list back. And that way, our lookup time would be basically the length of the prefix, right? It would be very efficient. But the problem is that at every node, we're storing a list of all of the children. And so that's not really efficient either. That's going to basically take us big O of the size of the dictionary times the size of the dictionary. Because you basically, for every possible word, you have potentially every other possible word as a child of it. And so that's going to take a lot of space, but it's going to be a constant time lookup. And then alternatively, we can say, okay, well, let me traverse down to the end of our prefix, and then I can just recursively go do like a depth first search and search for all of these marked nodes, all of these nodes that mark the end of a word, and then add all of those to a list, return back up, and then return that whole thing. And that's going to take linear time in terms of the length or the size of the dictionary, right? Because the worst case scenario is we have this empty string, and then we just traverse through all of the possible subtrees to find all of the possible words. And so that's not ideal, but I think that's better compared to the space complexity. So that's how I'm going to solve this problem. And I understand that that was a lot of information. So now we're actually going to go ahead and code this up. And hopefully this is going to become clear if anything was less than obvious from the first time around. So we're going to start by creating our node class. So I'm just going to call this node, and it's going to have 3 fields in it. First, I'm actually going to store, rather than storing the character that node represents, I'm actually going to store the entire string up to that point. So that when I'm traversing my tree and I get to a terminal node like this, I can just return the value right back. I know that the string that path represents, I have that right there, rather than me having to actually keep track as I traverse through. And it's just going to make the logic slightly simpler, so I prefer that. So I'm going to have a string prefix. And then next, what we need is a hash map or some way of storing all of our children. And so I'm going to create a hash map of characters to nodes. And I'm going to call this next, or let's call it children, because they're all the child nodes of our tree, of our specific node. And then finally, we want to be able to mark the node. And so I'm going to call that, it's going to be a Boolean, and I'm going to call it isWord. And that's going to mark whether or not this is like the terminal node of a word. Because otherwise, let's say that this node wasn't marked, we would have no idea that this A by itself was a word. If we don't mark this node here, then you can only distinguish the nodes or the words that are all the same length, or you can only distinguish the words that end at like a terminal node in the tree or a leaf node. So we need to be able to mark that, and so we will do that with this isWord. And then I'm also going to create a constructor just to make this a little bit easier. I'll call it, it'll take in a string prefix, and it's just going to set this dot prefix is prefix, and it's also going to, I'm going to go ahead and initialize our next our children map. And you could do that lazily, but it's just a little bit, it's one less thing for us to worry about later. So certainly something you could do might be, it would save you a little bit in terms of memory usage potentially, but I'm not going to worry about it. So I'm going to say this dot children is going to be a new hash map. All right, so there's our node class. And now what do we need? So I should also probably, this is going to be a actual public class here. Since normally I would just, show you the single method, but since we're actually doing a full object here, it'll be helpful to see it in its context. Then what we're going to need in our object is a pointer to the head of our tree, right? So, or our try. So I'm going to have a private node try, and then let's go ahead and just start with my constructor. So I'm going to have public autocomplete, and it's going to take in a list of strings, which is our dictionary. And then let's actually go ahead and add our other method as well, just so that we have a record of it. What we need to implement, we're going to return a list of strings, and this is going to be called get words for prefix. And it's going to take in a prefix. So, okay. Now here for our constructor, I'm going to implement a method that's going to just insert a string into the try. And that way our constructor is just going to loop through all the strings and insert them all into the try. So let's go ahead and we're going to say, first our try is going to be equal to a new node. And there's obviously, that's, the empty string at this point. So there's no prefix there. And then I'm going to say just for string s indict, insert word. And then what I'm going to do for my insertion, it's going to take in the try or the node that we're at. And then it's going to actually, we don't even need that, right? Because we are just going to take in the word itself. So let's go ahead and say public, it's going to return void, insert word, and then it's going to take in our string s. And actually this should be private, right? Because this is going to just be one of our helper methods. We're not actually going to expose this. So it's going to take a word, and we can just loop through the characters of the word, right? We're going to loop through, and then each time we're going to check if a node already exists for that character. And if the node already exists for that character, we're just going to go ahead and iterate to the next node. And otherwise, we're going to insert a node for this character. So we're going to have a node cur equals try. So we're starting at the top. And then we're going to say for int I equals 0, I is less than s dot length, and I plus plus. So we have two cases, right? We have the case where the node is already in the try or the node is not. And so we're going to say if, let's start with if it's not, if n.next, or sorry, n.children dot contains key. Because we're going to look if the character is in the list of children or not. So if n.children.contains key, s.car at I, then we are going to, so this is the case where it does not contain that child yet. Then we are going to add a new node. So we're going to say, or this should actually be cur, right? Cur.children dot put. We're going to, the character is s.car at I. And we're going to create a new node. So we're going to say new node s dot substring 0 to I plus 1. And the reason for the reason why we're doing the substring is that we want to get the prefix of, or we basically want to get the part of this string that we've seen thus far, right? And then we need to do the I plus 1 because the substring is inclusive of the first value and exclusive of the last value. So we want to make sure that we get up to and including the current character. So we're going to put that into our list, or into our hash set. And now we want to do two things. One, we want to move to our next, we want to basically increment cur. And we also need to, if we got to the end of a word, we need to mark it as such. And so if we are currently at, if I is equal to s.length minus 1, then we know that this is going to be the end of a, and actually this should be function. Then we know that we are at the end of the word. And so this is primarily useful for the case where if we're, in this case that we looked at where we reach the end of the word here, but there's still more nodes to go. Otherwise, we could just say, the last node is always marked as true, but we will just do that manually here. So we'll say that cur equals cur.children.get s.car at I, right? So we're just, in this case, we are putting it and then we're immediately getting it back again. But in the case where it was already in there, we're going to get it for the first time. So this just, I think, simplifies the code a little bit. It's a few fewer lines, but it's maybe slightly less efficient. So, it's up to you. And then we're going to say if I equals s.length minus 1, then we're going to say cur.isWord is true. right? So we're just going to mark it in that case. And so that's our entire insertion. And now the next part that we need to do is to implement our get words for prefix. And so now that they're already in the try, we just need to look up the words. And the way that we want to do this is we want to start by iterating through to the end of our prefix. So basically, we're going to find right off the bat, if the prefix is not even in the try, then there are no words that start with that prefix in the try, so we'll just return early. But otherwise, we're going to iterate to the end of the prefix, and then we want all of our options that are children of that node, right? So we're going to we're going to create a method that's just going to recursively go through all of our subtrees and find every word that is a child of that node at the end of the prefix. So we can do that pretty simply. We're just going to start. We need to create a list of our results. And then I'm going to iterate through to the end of, I'm going to start by iterating through to the end of the prefix. So I'm going to say node cur equals try, and for car C in prefix dot to car array. And then here we're going to say that if the current dot children contains the key, contains the character, then we know that they're still nodes and we keep going, and otherwise we don't have the prefix in this try, so we're just going to return null, or we're going to return the empty list. So we're going to say if cur.children.contains key C, then we are going to say cur equals cur.children get C, and otherwise we're just going to return results. And then I'm going to implement this method that I've been talking about that's going to be, I'm going to call it find all child words, and it's going to go recursively through and find all of the words that start with that prefix. So I'll just go ahead and call that here. It's going to be just find all child words. And this is going to take in our current node. Since we're doing it recursively, our current node is going to change. And then it's going to take in the list to add our results to. And then after that, we just return results. So finally, all we have to do is implement that recursive method. So I'm going to say private void find all child words, and it's going to take in a node n and a list of strings called results. And all we have to do is say, so first we want to check if our current node is like the end of a word, right? So we're going to say if n dot is word, then we know that the value of that, the string prefix, or this string here, then we know that that is a valid word and is a word that we want to add to our list. So we're just going to say results.add n.prefix. And then, once we do that, we want to go through all of the children and recursively call all of the children. So we're just going to say for character C in n.children.keyset. So keyset returns a list or a set of all of the keys in the hash map. And then just for all that, we're just going to recursively call it. So we just say find all child words, and we call it with our n.children.getC and results. And so of course this is you're ultimately going to reach some node where there are no children, and so that's going to terminate our recursion. And so this is a decent amount of code, but that's the entire problem here. So let's go through a very simple example. We will reduce maybe this example down to something a little bit smaller. So let's just take these 3 words. So this will be our dictionary. So we're going to go ahead and pass this into our autocomplete. So we'll say that we end up with, we're going to start by creating a node whose value is going to be the empty string, and then is going to be this hash map is empty and isWord is false, right? So that's what we're going to start as, and then we're going to say insert word. In this case, our dictionary was this, so we'll start with def, and we'll say node cur equals try. So cur is going to be equal to this, and then let's say I equals 0, and I is going to be less than s. In this case is def, so s equals def. And so we're going to say if current.children.contains key, it does. So in this case, children doesn't contain any keys. So we are going to return, this is going to go into here. We're going to put car at I, and then we're going to say new node of substring from 0 to 1. So the value is going to be D, and so we're going to have a substring whose value is D, and then the children is obviously empty, and it's going to be false, and we are putting that at s.car at I. So we're going to have one of the characters is going to be D, and that's going to map here to this node. And this is going to be a little bit tricky to represent, but we'll do our best here. So let's go ahead and just say like this, and I'll put a D next to here to make it clear what's going on. And then we're going to do the same thing for the next character. So we're going to say E, and then E is not, so I is now 1, E is not in it, so we're going to add E here, and then we're going to add another child, which is going to be E, and again this is going to be DE, right? Because we're taking the substring from 0 to 2 now, and so DE and empty and false. And then our last iteration through, we're going to add F here, and we're going to say that we're going to, again, it's not in our list, so we're going to add it. We're going to add F, and it's going to be right here. And now we're going to, so initially we'll set this to false, but now we're going to say that if I is equal to s.length minus 1, which now I is equal to 2, then is word is going to be true. And we're going to repeat this, and I will not go through all of this because this is going to obviously take a long time, but I think it's a good exercise for you to go through on your own. And in the meantime, though, let's just go, and I'm going to go through the rest of I'm going to go through this get words for prefix. So let's consider that we have just the word AB in our try. So we're going to have AB and we're going to have A. So we have basically our empty node here, and then this is going to have A in it, and then it's going to be false. And then we're going to have one child, which is going to be A, and this is going to be B, and true in this case, right? Because we have the word that's just A, and then again we have AB. This is going to be empty, and it's going to be true again. So let's look at it. If we were to look up, let's start with a word that we know is in here. So A is in here. We're going to call with A, we're going to say that C equals A in this case. And so current.children.contains key, so this contains A, so we're going to say current is now here. And now we come back, we break out, and we say find all child words for current. So we're going to call on current, and then it's going to say if this is a word, which is true. So our results, we're going to add A. And then we're going to call this recursively. So we're going to say for all child keys, so in this case we have B, we're going to say n.children.get B and results. So we're going to pass this in here, and it's true. So we're going to, add A, B, and then we're going to return this. And so again, you could go through a more detailed example on your own, and I highly recommend that you do that to make sure that you fully understand this. And as always, all this code is going to be on the website. So hopefully that was an informative problem for you. That's a bit more involved than some of the ones we usually do, but it's definitely good practice. And it's good practice in terms of object-oriented design and thinking. So I highly recommend going through this problem and making sure you understand it. And if you have any questions or comments or anything, let me know in the comments below, or pop over to the blog and let me know there. And I will see you guys again soon.